Hello, everyone. Welcome to another episode of the MATLAB and Simulink Robotics Arena. For today's episode, we're going to talk about optimizing airframe sizing using genetic algorithms from the Global Optimization Toolbox. And to join me today to talk about using this genetic algorithm for this particular purpose, I have Joshua Williams from Cornell University. Hello, Joshua, and welcome to the MATLAB and Simulink Robotics Arena.
How are you? It's good to be here.
Awesome. So moving on to today's agenda, Josh is going to cover the basics of airframe sizing, and then he's going to talk about how he used the genetic algorithm for optimization. Following which he will do a software demonstration, and then we do some key takeaways as usual, and point you guys to some resources that you can use to do better at your competitions. So without further ado, I'm going to hand it over to Joshua and let him take it away.
So CUAir is Cornell University's Unmanned Air Systems team. At Cornell, we have project teams, and we are a team that compete in an international competition every year hosted by the AUVSI. It's called the SUAS competition, where we have to design and build an autonomous aircraft that is capable of autonomous takeoff, waypoint navigation, landing, and we're getting into autonomous imaging of targets and autonomous detection, localization, classification of targets on the ground. So we have about 50 plus members, maybe 20 being mechanical engineers, 20 being software engineers, and a select number of ECEs and other majors. So we generally do very good in the competition. We've placed second internationally the past few years, but the what we have to do each year, what we decide based on previous years changes. So sometimes we might change our camera or decide to use a catapult in the picture as shown. So the way that we design our aircraft changes, and this lends the need to have a quick way to plug in our new parameters and get an airframe out that'll act kind of similar to the previous one. And that is where MATLAB really helps us out. So before we get into the code, I just want to talk a little bit about the basics of airframe sizing. So when you're sizing an airframe, it's very much an open-ended design problem in that you kind of change a variable and then everything else changes because of that. There's no one set solution that says you can't just pick one that'll perfectly fit all your variables. You have to do a few different things like, so we define the wing planform area first based on how much you need to lift and how fast you're going. And then you get into defining your aspect and taper ratios. And then you need to determine the stability of your aircraft. So static stability being on your pitching axis and spiral stability being on your rolling axis. And then kind of after that, you figure out your tail distance and sizing, and then your tail provides some negative lift. So you need to go reiterate your wing area. And the whole process becomes this very iterative, open-ended design that's not easy. It's not easy to do by hand, and you have to do a lot of iterations. So having a numerical tool to help out with this is really helpful, and obviously MATLAB makes this a lot easier.
So Joshua, just before you move ahead, this this particular problem that you were describing, it seems like a lot of variables and a lot of moving parts. Have you tried multiple strategies to design these aircrafts, or was this genetic algorithm like the first stop for you guys?
So first we did it by hand, and we were kind of writing stuff out, and then we got to the point where we had to put our tail in and realize that it took away some lift, because the way that we design ours, we have our tail provide negative lift, and that's for reasons I'm not going to get into, but it detracts from the overall lift of your aircraft, and then you have to restart. And kind of the first time we went through that whole cycle, we said, man, we should just use a computer for this instead. So we started putting stuff into MATLAB and running through that iteration manually and taking the old values and plugging them back in. And then we said, you know what, why don't we just automate it and make some kind of algorithm choose a variable for us, a value for us. So yeah, I guess we did try it by hand at first, and that's how we figured out what parameters we wanted to determine. And then from there, it was just easy to give it to the computer and have it make things a lot simpler.
Interesting. Yeah, I mean, it really does make sense. Why would you do something that a computer can do quicker, right?
Yeah, exactly. So we used the Global Optimization Toolbox, which is a nice package inside of MATLAB. And we just defined 4 parameters that we knew were the most important to our aircraft sizing and then iterated them. So basically, we'll get into the actual parameters once we do the technical demonstration, but it's wing area, static stability margin, and then the tail distance, and then I believe the tail size. So we tuned a fitness value based on how well our airframe that this algorithm figured out fit certain parameters that we wanted to keep. So how well did it fit how much lift we wanted? How well did it fit our static margin and stuff like that? And we set very large bounds on the key parameters, and then let MATLAB do all these iterations. And you can see on the right side of the screen, it kind of is going through and defining based on the fitness value, iterating down to a lower fitness value, which is better. And eventually we give it a cutoff and it says, all right, this will work.
Okay. If I picked up on that right, what this means is you can basically define any parameters that you're trying to optimize. So it doesn't necessarily have to be the 4 parameters that you sort of mentioned. It could be pretty much anything that you're trying to optimize.
Right.
Okay.
Like we knew we wanted a certain aspect ratio, taper ratio, and dihedral. So we fixed those and then figured out the wing area from the algorithm.
Okay,
and
cool.
Stuff like that. Because a lot of those like geometric parameters like aspect ratio, taper ratio are kind of just defined, and you look in a book and it says this is a good value for this kind of aircraft. And we wanted to fix some variables because if you give it so many possibilities, it's hard for it to come up with one. Correct. So you have to kind of fix a few, which we'll get into in the code. We wanted having to do that. Yeah.
Okay, cool.
All right, so now we're going to get into a demonstration of the software. Cool. All right, so I think a good way to do this is, well, why don't we just run it once, see what happens, and then we'll go through it.
Yeah,
so this is the aircraft designer file, which is the main runner of the whole thing. And you can see, if I scroll down a little bit, the lower bound and upper bound of the parameters we're trying to set are right here. And this is the wing area is the first one. Then the static margin is the second one. Horizontal tail moment arm length is the third. And then the horizontal tail angle of attack is the fourth. Okay. I think before I said it was the area, it's actually the angle of attack.
Okay.
So we give them each pretty large bounds except for the tail moment arm, and that's due to the physical dimensions of our aircraft. We have a boom that we have to put everything on that has like certain length. So we decided to just fix that one thing because we knew how long we wanted them to be apart from each other. Yeah, now that we've looked at kind of what the bounds are, what the parameters are, let's run the software and see what happens. Just give it a second to load up. There we go. All right. So you can see how it is iterating lots and lots of different aircraft configurations, and there's kind of a general downward slope in the fitness value, and once it gets to a value below a certain threshold that we set, it's going to say, all right, we finished right now. So right here it tells me the 4 values of the parameters, and these are kind of the 4 most important things that we want to put into our design. And it also just gives us everything we could possibly need. So, why not have all the data? A lot of this stuff, if you go up to, I'm not sure if it's up or down, because the side of my screen's cut off a little bit. But yeah, you can see wherever it is, the wing span and sizing is kind of the most important for our design stuff. So like wingspan being that, and then you get down to like horizontal tail sizing and like root and tip towards the horizontal tail and the length of it. Those are what we really take and put physically build. So it's great because it just gives us all the values we need, and we can go ahead and build that and know that the math checks out and is confirmed by these calculations. Yeah, so why don't we go back to the code, and we can look at the other builder files that we've used for like behind the scenes. Yeah. So getting into this long stability fitness value, this basically is the file that assembles all the other .m files and figures out based on a fitness value what the best case is. So the fitness is pretty much defined by these. So I'll start at the beginning. All right, so first we just pull in the parameters, which I believe are right here. So it just brings in, these are constants and just like general specifications. So like we know what the mass is going to be, flight speed, the desired static margin and pitching moment that we want to have. And then stuff like our aspect ratio, taper ratio, dihedral. This was all stuff I was saying that we pretty much know we want to keep it the same. Yeah. So, and then this is just characteristics of the airfoil and stuff about the tail. Yeah, so that is all just pulled in. And then we extract the variables, which we want to change, being the 4 that we talked about, the 4 that are output at the end of the aircraft designer. And then that's based on X, which it gives it the range in aircraft designer. Then it goes into the calculations right here. And this is where it actually says, like, okay, what are the root core going to be, tip core going to be, and all this kind of stuff, such as a Reynolds number calculation, so tail sizing.
So these are basically all your aerodynamic calculations, the actual the meat of it, so to say.
These are the equations we did by hand the first time, and then realized we didn't want to continue doing by hand. It's this is pretty mathy, but once we do it once, we don't have to do it again.
Yeah,
which is nice. And then the metrics are just kind of evaluating how well did we do in, like, where is our CG, what is our lifting moment, pitching moment, and calculation of static margin, spiral stability, and then how much lift and excess lift do we have. Excess lift is just based on the weight. Did we do too much? Like, are we going to get a little more lift? And generally, you get that number down to 0. So once this calculator here figures all that out, it goes and it finds pitching moment, fitness value, static margin, fitness value. These are basically just deltas of the total pitching moment minus the desired, and then static margin minus desired static margin. And then, as I said, lift fitness, which is the excess lift squared. The stuff like squared and then these values in front of them in the fitness value are all kind of tweaks we made because we just wanted to put more weight on certain parts of it. Like, we didn't want to have really any excess lift. Correct. And then we wanted to really stress pitching moment and static margin and stuff like that. So these kind of define the feel of the aircraft.
So basically, these fitness values are things that you guys have sort of decided and said, okay, this is what we want our airplane to do at the end of the day, and these can be modified, and they would give you different parameters to your aircraft.
Right. We played around with these a lot and found like areas that we wanted to stress, kind of comparing to existing airframes and stuff we've built in the past, because we built aircraft before we made this code. And you kind of just get a feel for, like, does that look right? Do the numbers kind of look like they make sense?
Correct, yeah.
So playing around with the fitness value and comparing it to existing airframes, we basically settled on these numbers that stressed the areas we wanted to stress and didn't place too much value on stuff we thought was a little less important.
And this is actually a good point to note for newer teams. This is where simulation plays a big role. I mean, teams like Cornell have been around for a while, and they have multiple airframes that they can compare things against. These values could potentially be put into a simulator, and you can figure out if your aircraft is performing like you want it to perform.
Yeah.
Okay.
Yeah. So, like, just going back to the variables. I think that the wing area is a lot more important than the tail angle of attack in some ways. Like having the range what we had on our wing area, changing your tail angle of attack by 1 or 2 degrees isn't going to destroy the aircraft, but changing your wing area by like 10% could have some pretty detrimental effects on how it flies. So I always say, and I'll talk about this after we finish the technical demonstration, but the fitness ultimately kind of determines the feel of the aircraft and like how it flies
Correct. Yeah.
from a more uh, objective point of view,
Hmm.
or sorry, subjective point of view. Yeah,
Okay. Okay.
yeah. So that's pretty much how the software works. It's not very complicated. I mean, it's not simple, but
Yeah.
it's compiled into these six programs, and
It's one of those things that require little investment to set up, but then could be used for multiple years going down. And all you really need to do is change these fitness values, and it's still going to spit out the same results at the end of the day.
yeah,
Yeah. Another thing that I wanted to ask you, so these genetic algorithms, just inherently the way they are built, if you run them multiple times, they actually give you, give you multiple results.
right.
And Josh can actually show that if he just hits run again, we can, you can compare the values and see that they actually, they're actually different.
Yeah. So
Yeah, it looks
let
like
me
you
go
ran,
back.
looks like you ran the wrong function there.
I did. There we go.
But yeah,
Yeah. So
it's pretty visible here that you can see that these sort of fitness value hits that are popping up on the graph are a lot different from what it looked like earlier.
definitely.
So how do you guys sort of deal with that? How do you all figure out what's, because I mean if this code is going to give you a different set of values every time you run it, you all have got to figure out a way to figure out which is the sort of optimal solution. How do you guys go about deciding that?
Yeah. So like you run it maybe 10 times or 15 times, or
Mhm.
sometimes you don't really need to run it that many times, but you run it enough times and you realize that the variables are going to come out to something that's pretty close to each other.
Okay.
So like next time we run it, it might be 6443 or like 6445, but compared to the total value, that's really nothing different.
Okay.
So they all kind of come out in a number that is pretty close to each other.
Okay.
And then from all those, you basically just pick something in the middle and use that,
Okay.
and
Okay.
it'll work for you.
Yeah, and I'm sure all of this really needs to, you actually need to design the aircraft and test it before you can sort of settle on any of these values. And it's always good
Yeah.
to test multiple configurations and see which one works best for you.
Yeah. Actually, so I just want to mention the person who added. I worked on this with a well, he was a grad student at the time, Derek Faust, and he was more involved in the global optimization part of it, and I was more
Okay.
involved in the where is it? Setting up all the big long equations in this file.
Okay.
But he kind of was the one who figured out like that if you run it a few times, you basically settle into
Ah.
the same
Okay.
value, and it's pretty good
Okay.
because yeah,
Okay.
yeah,
Cool.
yeah. Big props to Derek for helping all this. Yeah.
All right.
So yeah, I mean, just the verification, we've used this and flown aircrafts with it, and found that we had steady flight, some smooth handling, and just a really beautiful flying aircraft. And also, as I was saying before, the fitness value qualifying the feel of the aircraft. So it stresses the same things. If you give the aircraft different configurations, like let's say we wanted to change the weight, but if we kept the fitness values, it still stresses the same parameters and would make the plane fly in a similar way. So
Mhm.
from a pilot's perspective, it would feel like a pretty similar aircraft to fly.
Okay.
And we think that this is a huge benefit of the program in that we can, because doing that by hand is really hard to do, maybe even impossible. But doing it with the code is as simple as keeping the fitness parameters and just changing some of your other constants, which is
Yep.
really nice. So some key takeaways. As we were showing in the variables before, we fixed the tail moment arm, and you can see in a cross section of our current aircraft right here. This rod right here is a carbon fiber boom of a fixed length. So if the code spit out that it wanted us to put our tail a foot back, you actually don't have the length on the boom to be able to do that.
Correct.
So
Yeah.
we had to fix that, and we kind of just found a value that we liked. Um, there are some texts that state that the wing and tail moment arm distance, so the tail moment arm is the distance between the wing quarter chord and tail quarter chord, and they say it should be around 60% of the fuselage length, so the total length for this kind of aircraft. So we just settled on a value around there and stuck with that because we were finding that running the code with that totally free, it would bottom out on one side of the range. It would either choose the absolute top value we gave it or absolute bottom value we gave it. So I think we had like incorrectly defined the parameters of the equation. But once we fixed that, it was totally fine. So again, it's important that the iteration is based on a seed value. You can't just give this program any number of values and expect it to come up with a solution, but giving it really wide range is like on the wing area, we gave it 0.5 meter squared to 1.2 meters squared, which is a huge range. And it found a value of, what was it, 0.644, which is like, you know, we gave it a very large range and it settles on a pretty good value. So, but it does necessitate giving it initial parameters, so having some idea of what you want to have in there, and that's done kind of from the first round of hand calculations.
Correct. I think that's something that you sort of just pick up over time, and just as you get more experienced with designing these kind of aircrafts, it sort of comes to you at that point.
Yeah, like everyone that had worked on this had experience designing aircraft in the past. Like the year before this, we did it by hand, and it flew fine. So, and then after, of course, we confirm it with hand calculations, kind of go through and just make sure that what the computer did was right, and it was, of course. But we just want to make sure, double, triple check before we put this thing in the sky. And we found that using the numbers that it spits out, the design is generally just better than if done by hand. It gives us more accuracy and more exactness on what we want to have as the airframe geometry.
Okay. Well, awesome. Thank you so much, Joshua, for sharing this information with us. I think a lot of teams can benefit a lot from this.
Definitely.
So finally, coming back to some robotics arena resources. Again, if you like the videos that we're putting out and you want to learn more, we're always looking for topics that you people are interested in. So please write us at the robotics arena at mathworks.com, or you could get in touch with us through our Facebook group, which is called the MATLAB and Civil Link Robotics Arena. We also have a web page where all these videos are hosted, and we've got some good content coming out, so look out for it. Finally, don't forget about the software offer. I know teams like Cornell and a lot of other teams that are very successful in these competitions do use MathWorks software provided through the student competition program, which gives you a lot of specialty tools that you probably won't find on your school licenses. And then finally, don't forget to visit our Racing Lounge blog. I know it sounds like a little bit of an automotive kind of blog, but it does include robots and it does include aircraft as well. So thank you so much, and we hope to see you again in the robotics arena.